The next talk is Unsupervised Discovery of Object Landmarks as Structural Representations. The talk will be given by Yuting Zhang.
Hello, everyone. I'm Yuting Zhang from the University of Michigan. It's my great pleasure to present our paper, Unsupervised Discovery of Object Landmarks as Structural Representation. An important goal of computer vision is to enable the machine to understand visual structures, such as object poses, contours, and 3D shapes. These structures are physically conceptualized and perceptible by humans. Deep neural networks have shown remarkable success in learning latent representations with many desirable properties. However, the structures of those representations are not conceptualized or interpretable. To bridge the gap between the latent representation and the explicit structure, supervised learning methods require extra human annotations. They are often costly to obtain and unavailable for most object categories. Then it comes to the question, can we use deep neural networks to learn image representations of explicit structures? To study this problem, we consider a particular type of structure, the object landmarks. We define the landmarks as the salient points that are semantically consistent across objects in the same category. They can encode the shape and pose of an object compactly, and they can be applied to many object categories. To extract the representation of an object, we propose a model to discover the landmarks as a structural component. Our model can also extract additional latent features based on the landmark locations, making the representation more informative about the object appearance. Taking the representation as an intermediate step of a bigger pipeline, we can optimize the landmarks and latent features for a downstream task. Particularly for unsupervised learning, we take the image reconstruction as a generic driving force to learn the representation. This leads to an autoencoder framework. Under this framework, we address the challenging problem of unsupervised object landmark discovery and make our model work for different object categories. The whole framework is realized by a fully differentiable neural network. In the backward path, the image reconstruction can encourage the model to learn informative landmarks and features. Now, we expand our framework to an overview of the neural network architecture. Let's nail down to the module for unsupervised landmark discovery. The key components are the differentiable formulation and the unsupervised constraints to define a valid landmark detector. Our model is inspired by Seungris et al. Study, but their formulation is not differentiable. Similar to a one-shot object detector, our object discovery module uses a convolutional neural network to get a detection heat map. The network has an encoder-decoder architecture with skip links. We normalize all the heat maps, including the background, using the softmax across channels. From each foreground heat map, we get the coordinate of a landmark. More specifically, we approximate the foreground heat map with an isotropic Gaussian. We take the mean of the Gaussian as a landmark coordinate. Essentially, it is an averaged coordinate weighted by the foreground heat map, and this is differentiable. But so far, the output of our model are not guaranteed to be valid landmarks. In other words, they can be arbitrary latent features without explicit physical meanings. We define three unsupervised soft constraints to make the landmark detector desirable. A good detection heat map should have its value concentrated in a small local region. We achieve this by encouraging the isotropic Gaussian variance to be small. And in the later training stage, the heat map can become more concentrated. Different landmarks are expected to localize different visual semantics. We penalize the model if the pairwise distances among landmarks are too small. The most important property of a landmark is to localize a visual semantic pattern stably. Suppose we have a transformation that is not destructive to the visual content. When it is applied to the image, the landmark should move accordingly to the same transformation. Only in this way, the landmark can localize the same pattern stably. This property is called the equivariance, and it can be constrained by this equation. Sungis et al. Used the equivariance for landmark discovery by defining a training objective on the detection heat maps. In contrast, we can apply the above equation directly on the landmark coordinates with the help of our differentiable formulation. Following Sungis et al., we use random simplet spline to simulate the image deformation. When videos are available, we can also compute the optical flows and use them as the transformation during training. With the above unsupervised constraints, our model can discover valid landmarks. Now let's move on to the landmark-based extraction of the latent features. Our key idea is to perform a weighted average pooling around the landmarks using differentiable masks. In more detail, we extract a convolutional feature map from the image. Then for every landmark, we take its corresponding Gaussian heat map as the mask for the average pooling. As an illustration, we pixel-wisely multiply the Gaussian heat map of the first landmark with all the channels of the feature map. We reduce the reweighted map to a single feature vector by spatial summation. We do the same thing to the other landmarks, and also similarly for the background. Putting things together, we obtain a stack of local feature vectors for the landmarks. After the feature extraction, the last component of our model is a landmark conditioned image decoder. It reverts the landmark localization and feature extraction. According to the landmark coordinate, we generate a Gaussian heat map with a fixed variance, and we perform normalization across channels. For the local feature of every landmark, we duplicate it at each pixel to get a convolutional feature map. We take the heat maps as the reweighting factor for the feature maps. All the reweighted feature maps are summed up together to form a single tensor. We also concatenate the heat maps to this tensor and feed it to another neural network for image reconstruction. So far, we have reverted the encoding procedure and complete the model definition. Now let's take a look at the key experimental result. For unsupervised landmark discovery, Sungis et al.'s work is the only one that we can compare with. Both methods can discover reasonable landmarks on facial images. However, their method can sometimes make significant mistakes. We highlight the incorrect landmarks with red circles and indicate the correct locations with green dots. These mistakes are mostly due to large pose variation and occlusions. In comparison, our method produces more stable results on the same images. Our method can also discover more landmarks on not well-aligned facial images, like this. We also evaluate our model on cat head image and on more objects, including shoes, digits, cars, and wild animals, and also on the human body. The human dataset has data in video format, so we use optical flow as additional self-supervision for the equivariance. The unsupervised structure discovery of complex objects like human bodies are very challenging, but our model can still get reasonable landmarks. To evaluate our method quantitatively, we train a linear regression model to map the discovered landmark to the human annotated landmark. So an ordinary landmark detector can be obtained without fine-tuning the neural network. On the MAFL face dataset, our model outperformed the single-cytose method, even when their method used more discovered landmarks or a dense object frame. And surprisingly, our method also outperformed the off-the-shelf supervised method. In addition, with only 500 labeled samples, our linear regression model can already achieve very good performance. This is a strong result for semi-supervised learning. For the other types of objects, our method can also achieve better results than previous unsupervised method. For more quantitative results, we evaluate the effectiveness of our discovered landmarks as visual features. In particular, we consider the binary classification of shape-related facial attributes. As shown in the table, the classification accuracy based on the landmark coordinate alone are pretty good. And this is better than using the pre-trained FaceNet features. Finally, I'd like to show that our autoencoder framework can naturally produce a good image generator conditioned on the landmarks. And our discovered landmarks are disentangled from the latent features automatically. In particular, we keep the latent feature fixed and manipulate the discovered landmarks to generate new images. As the figure shows, the facial shape, expression, and pose make changes according to the landmarks. The other appearance factors are kept the same. And here is another example. And it also works for human body images. To conclude, we address the challenging problem of unsupervised object landmark discovery, and we formulate it as a sub-problem of representation learning with explicit structures. We propose a fully differentiable neural network architecture to tackle this problem. And our unsupervised model can produce meaningful landmarks, show competitive performance to supervised facial landmark detectors, and provide a neural network interface that the human can manipulate. With that, I hope our work can inspire more studies on the unsupervised learning of perceptible and interpretable structures. Thank you very much for your attention.
As we handle questions, would spotlight presenters please start lining up by the stage? We have very limited time to change between spotlights. Any questions? Okay, let me ask a question. Your work, as you mentioned, was inspired a lot from the work by Thulis et al., and you showed pretty significant improvements from their approach.
Yeah.
What aspect of your model did you find most important for those improvements?
I think actually several aspects. The first thing is we have a fully differentiable formulation. It actually makes the definition of the unsupervised learning objective function much easier, and I also make it much more effective. And we also can get training signals from the downstream task, that is the image reconstruction, which is also useful. And finally, I believe we also use a stronger neural network architecture, and our architecture can capture a little bit higher level information. And this is also helpful for the landmark discovery. Yeah. Thank you.
Let's thank the speaker again. Oh, actually, there's one more question.
Hello? Yeah. So first, I'd like to say this is a really cool paper. I really enjoyed it. This is very neat and kind of a, out of the box. But I was wondering if you have thought of making it a little bit more out of the box even. You're assuming that these the features should be X, Y points, right?
Right.
Is that maybe we should get rid of even that assumption? Maybe they should be lines or curves or I don't know, smiley faces or
Right, yeah.
Is there any reason they have to be XY points?
No, it don't have to be XY point. Actually, I also thought about similar problem to make it line or something, but XY point is the simplest. So this is my first paper about this in this direction. So actually, in the future, I think it will be quite interesting to consider other maybe geometry or even some geometry in the high-dimensional space. I think that will be an interesting direction. Yeah. Thanks.
There's actually one question on this side before we end this session.
Yeah, so I have another question about, so for unsupervised landmark detections, you have three criteria how to suggest a good landmark. One of them is all the landmarks should capture different semantics.
Yes.
So you penalize that with the similar semantics.
Right.
So my first question is, how did you select those three landmarks? And the second is, when you have this type of penalize, does this your work on, say, outdoor structured data set, those kind of images?
Yeah. So your first question is the number of key point or something?
So the number of the three unsupervised constraints that you use for training the landmark.
Okay, your question is how I designed this three?
Yeah.
Okay, sure. Yeah, so for the landmark, the equivalence is the most important thing. Yeah, so this is something quite apparent, and we must do this. But if we only do this, we can get some trivial solution. The first constraint is a concentration constraint. If without that it's possible, we can get two peaks or multiple peaks on the heat map, and in that case, my formulation will not work. So the first constraint is to make the heat map to have a single peak. And for the second is a separation loss. The separation loss is necessary because in the beginning, your heat map is random. And for random heat map, all the landmark, remember that they are the mean coordinate. They are all around the center. So they have similar initialization. So in this case, if we just train the neural network, we can have a very bad local minimal. That is, all the landmark will just exactly at the center of the image. And this separation loss can avoid this kind of local minimal. Yeah. And for your second question, can you remind me?
Yeah. So if you have the penalty term for penalizing semantically similar landmarks, how well does your method will work on the building data set, for example, outdoor landmark data sets?
Actually, I haven't tried that. Yeah. So I don't think I can give you a definite answer on the building data set or this kind of thing. Yeah, but basically, the assumption is all the object instance should share some similar architecture. If they are similar building, probably it can work. But if they are quite different building, maybe not. Yeah.
Thank you.
In the interest of time, let's thank the speaker again.